modality. So you would say, well, the sensors come with the calibration formula. This is what comes from the manufacturer. And I can show you that here on the right side, if you apply the calibration camera formula from the manufacturer, you will get readings that have very wide spread. So still after you use that formula, you get very wide spread, and you have to calibrate the sensors. Now imagine if you are deploying millions of these sensors, you have to take each of them, put it on the interface board, program it, calibrate it. Once you are finished with the calibration, take another one and do the same. Millions of them. So what we proposed is, well, if you take the thermo-infrared camera and you calibrate that one, which we've done in the lab, then you can take a picture, and you have millions of them, or I don't know how many, would fit into your field of view, and in one snapshot, you can calibrate all of them. So I think that might have a significant application for the sensors. On the other side, if you say, okay, now I calibrated all my sensors, I want to calibrate my camera, you can, just a second, you can more or less put the sensors in your field of view, and repetitively, you can calibrate your thermo-infrared picture. Yes, please.
Before you deploy the sensors, you program them, right? They are pre-programmed, right?
Before you deploy them, you have to program them.
So why don't you calibrate them while you are programming?
Calibration, okay, so how would you calibrate them?
Like if it's a temperature sensor, you can have like 4 or 5 temperature points, and then you can calibrate
right.
when you are programming.
Right, but remember that in these days they are working on the wireless programming interface, so you don't have to put them on each. So, okay, so there are two things. If you put them on the interface board and you are programming, you are saying that at the same time I'm going to vary the ambient temperature and collect maybe 4 points, do the least square feet, and then kind of calibrate them. So that's one approach. But still, you don't want to do it for million sensors. In our experience, we really want to spend the least amount of time reprogramming them. And the calibration software that you upload might be very different from the operational software that you want to upload. So that was the motivation for that. I have not used the wireless programming capability for these sensors, but I know that Berkeley has been working on that quite a bit. And whether it's used, how much you can use it, I don't know. But we are thinking about these two different approaches how to calibrate whether sensors or the cameras. There are many, many, many basic questions when it comes to optimal sensor network design, and I'm just listing some of them. Is there an optimal spatial arrangement of sensor networks? We look at the linear arrangement, circular arrangement, and so forth. What is the impact of other wireless devices on sensor networks? We did the experiments. What if you have your cell phone on and suddenly all the experiment would report would fail? What is the dependency of wireless loss on the number of active sensors? We actually were probably, nobody really wanted to hear this, but we actually measured that as you are adding more and more sensors in your environment, you will incur more and more loss. But people didn't want to hear that. What is the most effective mechanism to receive information from the wireless sensor network? And the complexity is pretty large because we played with about 4 different communication protocols just to figure out, should we buffer more? Should we send immediately? Sending is expensive. It's going to drain the battery. And then, where is the trade-off? How do you synchronize data acquisition? I already addressed that issue. How to maximize information content of received sensor readings? Well, I might not want to send the timestamp, but then what's the value of that measurement if I don't know when it was taken? How often should one sample? What are the trade-offs, sampling rate versus wireless loss? How to preserve energy? So there are plenty of research topics. And I'll just show one of them that we kind of looked at, and that's the sampling. Clearly, if you increase sampling, you get more and more measurements, but suddenly you have more traffic. If you have more traffic, you will start to lose packets. And at some point, no matter how much you increase the sampling, you will not be getting back the samples because there is so much traffic and so much information loss. So again, what's the trade-off? How do you design such a system? And again, on the left side, I just listed the wireless challenges. OK, so now let's suppose we set up the environment and we want to go to an operational mode of the system. And one example is the camera control. You want to perform continuous low bandwidth data acquisition using MICA sensors to monitor fire hazards, and then trigger high bandwidth data acquisition using thermo-infrared or visible spectrum cameras to recognize types of fire hazards. And again, the past work is primarily in the surveillance applications, and Berkeley has done some experiments with air conditioning and lighting systems. Our proposed approach was just really to focus on the bandwidth control and then figure out the proactive camera selection. And the logic is very, very simple. More or less, if the light is on, then turn on the visible camera. If the light is off, then turn on the thermo-infrared camera. And you can see the interface here. More or less, we just want to report to the operator what's the temperature, what's the light, and then we would clearly show just one of the video streams. Hazard analysis. Okay, so now we want to detect the hazard. And the problem, there are many, many variations of this problem. You can go and scan indoor environments for hazards on a regular basis. You can acquire video and then search for hazards. Excuse me. And then if hazards were found, then identify the source. And our approach was to take the color and the temperature-based hazard detection and potentially use the spectral image analysis to understand hazards. So here is a video of the algorithm that we implemented. So if a robot walks into a room and we had some candles on the whiteboard, and as it goes, it is color-based detection of the places that form a hazard. And then it would report to the operator, here is the location. And not only that, but if you want to deploy a robot, and while the hazard is small, you might want to contain it. Excuse me. You want to know the orientation and the location and so forth. The human alert was another issue because when the operator is not paying attention, he might miss the information that there is a hazard. So how do you redirect his attention to the hazardous situation? And then right now we just created a simple overlay so we can show that there is some kind of hazard. Potentially there can be a beep or something like that. And then eventually the whole system would have a little bit more complicated human alert logic where when the temperature is higher than some threshold and the light is on, then turn on the visible camera, overlay the hazard, the region, and then maybe beep so the human is alerted. And if the temperature is larger than threshold but the light is off, then it would show the thermal IR camera output and the overlay on that. We are very interested in hazard understanding. We've done a lot of work in the past with hyperspectral camera. And the basic question is if you take a picture with the Canon camera and a Sony camera, what is the true red color? Because when I'm looking at fire and I'm trying to understand what is burning, I'm really basing my conclusion is based on the color. But do I know what's really true red, true yellow, and so forth? And I bet you that if you have two cameras, they will give you different values. So we did some work. We used the hyperspectral camera to establish ground truth, and then we can use the ground truth for calibrating single RGB cameras. We also went back to Maxwell equations, and actually the work that we did for a scene modeling project, which is shown on the left side, if you can get a very good representation of multiple fires, and you can build a database, then you can even predict how that fire is going to look and eventually classify the fire based on the appearance. And what is shown on the left side that we build this is called a bidirectional texture function, and a database of that for multiple clutters, scene clutters. And then from measured images, we can predict images once we know the layout. But unfortunately, we didn't finish this part because it's really, really very hard problem. But we want to be able to discriminate a fire of a sofa, which is hazardous, as opposed to a fireplace where you might have a fire and it's not a hazard. Hazard confirmation. So again, the motivation is to confirm hazard when